Line integrals. Let f be a continuous function with a domain that includes the smooth curve C with parameterization RT with t between a and b. Then the integral of c of f ds, and that means the function with respect to the change in the arc length, is equal to FRT magnitude of r prime t dt. There's a few things I want you to see here before we move any further here. Notice that I'm plugging in the RT into the f. So that means this would be a function with variables t in it. Another thing I want to point out to you here is that when I look at this magnitude of r prime t dt of what that truly is, if you remember, the integral of r prime t dt is, so that was our arc length. So S equals the integral of magnitude of r prime t dt, which was earlier in the book. So this here being our arc length, and when I plug that RT into the function, this here being my height. So let's take a look at a picture here. So think of this curve C down here on the XY plane, and then think of a function above the plane. And what we'll see here is this is our length and this is our height. So we're looking at an area integral here. So then if I project this curve up to the surface here, and I look at whatever that curve does on there, so it curves around. It could do a little weird things just because the way it interacts with that surface. And what we would be computing here is we would be computing this area. So in some books, they refer to that as like a curtain, the area of a curtain, because it's being projected up to the surface. And then in the process of that, it's creating that area. And that area is what we're calculating here. So evaluating a scalar line integral, that's what we're calculating, that area above the curve up to the function, or the surface of the function. So looking at the theorem below that one here, it really gives you the intuition of what we're dealing with. Now the picture I drew could resemble this one down here, where this one says f of x, y, ds equaling c, now down here, equals the integral of FRT, which that would be my height again. So that would be my height up here, of where each of those points goes up to. And then the square root of x prime t squared plus y prime t squared, that's what my magnitude of my r prime t is. So if I can just remember r prime t, this formula down below I don't have to memorize. But if I know this formula up top, because the r prime t comes up so much, like with tangent vectors and all that other stuff, it's probably a good idea just to realize immediately that r prime t is either this here, if I'm 2 dimensions, or this one here if I'm 3 dimensions. So those are things to consider as well. And that's all that is. This theorem below here really just breaks down the original statement that's above it here. So just keep that in mind too. And remember that S is equal to the integral of the magnitude of r prime t dt, and that's just this piece right here. So that's this distance down here at the bottom of my curve. That's what that is. So again, that's what we're dealing with here with these. So let's take a look at one of these problems now. This problem says, for the following exercises, use a computer algebraic system to evaluate the line integral over the indicated path. We're going to actually just do this one by hand. And one thing I want you to see first is notice this curve here. This curve and z equals 0. This curve is on the xy plane because my z is 0. And this curve is line because notice 1 minus t is linear. T is linear, so it's just going to create a line. And then this is going to be the height of that line. So it's an x and y. So this is just like the example I showed on the previous page, well, at least the setup of the previous page, where my line is in 2D, where it's in the XY plane. It's not 2D, but it's 3D. It's in the XY plane, and then it's being projected up to the surface x plus y. So we're just going to work on this integral now. Now this here says, hey, I'm going from this point 0, 1, 0 to 1, 0, 0. And notice here the z's are 0 for both points there, which makes sense because it says my z was 0 here. So everything should complement itself too in that same way. So what we're going to do is we're just going to set up this integral and evaluate it. So right away we can see that our RT is given to us. Anytime we see the parametric, we know that we have t comma 1 minus t, and that's my y. So there's my RT. And when we look back here, that's this curve down here at the bottom. Now again, it definitely doesn't look like that, but ours is a straight line. So now let's set up our integral. So since we're 2D going into 3D, because we're going to project it up to the surface of the function, that means we're going to use this formula down here. So that's going to be FRT times the magnitude of R prime t. And that's the one we're going to use from A to B. Okay, so our bounds we'll worry about in a minute. So our F here is x plus y. So we're supposed to plug in our variables for that. So my x is equal to t plus my y is 1 minus t. And again, I just pulled those from this x and this y that I see here. And z doesn't play a role in this because we're on the xy plane and we're projecting up to the surface. So the xt is, or the rt, excuse me, is going to be a dimension less. All right, so there's my f. And notice here, now go back, my operation between these, since I don't see anything, is multiplication. So the only thing I have to be careful of when I set that up is that I put parentheses around it, because now I'm going to talk about my r prime t. So before I write that r prime, magnitude of r prime t, but before I write that in there, I'm going to just do this. I'm going to find that derivative. So r prime t then is going to be 1 comma negative 1. Okay, so I'm going to put in here, well, actually I'll just find the magnitude here so that I can just put the number in. So the magnitude of r prime t is equal to the square root of 1 plus 1. Hopefully that's okay with you, because a magnitude is where I just take that component and square it, plus take the other component and square it, and then I square root it. So this is going to be the square root of 2. So I'm just going to put that here, the square root of 2, and then dt. Now what I have to consider is what are my bounds for this? So how is that going to work for me? So if I plug in 0 here, that's going to be 0, and it's going to be 0, 1, and then my z is always 0. So that's going to be my first point if I plug in 0 for t. Now that's what I have to be a little careful of here to make sure I do that correctly. So when I plug in 1, let's see what happens when I plug in 1 then. So my x is going to be 1, my y is going to be 0, and then my z is always 0. So I can see that my t is actually going to run from 0 to 1. So there's our setup, and that's it. And then from this area that we get here is going to be the curve, which is that straight line here. That straight line is going to be projected up to that surface there, and that's going to create that curtain look that we see over here on the right. And with that curtain look there, that's the area that we'll be calculating here. So then to do this integral, this is 0 to 1, and I'm going to clean this up on the inside here before I multiply by root 2. And what I'm going to see there is those t's are going to cancel. I'm just going to end up with 1. So 1 times the square root of 2 is the square root of 2 dt. So when I integrate the square root of 2 with respect to t, I'm going to get square root of 2t from 0 to 1. So then I put in my upper bound, when I plug in a 1, square root of 2 times 1, because I have to put a 1 here, minus square root of 2 times 0, which is 0, so I get the square root of 2 as our answer here. So there it is.